Hello. Okay, I'm going to try and make this video a bit shorter than the last one. So let's jump right into it. As a reminder, we're going to work through each one of these phases in sequential weeks. All right, we'll have another one just dedicated to evaluation. So we're up here in the idea development. All right, so much of what we're talking about here is kind of these meta concepts associated with defining a problem and the things that we would consider in data science as it relates to defining that problem and getting to know our data. Okay, the first thing to know is that much of data science, almost all of data science, is not interested in inference, but focuses on prediction. All right. Think of inference as kind of traditional statistical measures where we're creating these perimeters. I'm sorry if you can hear my dog backing in the background. Traditional perimeter measures, and we're doing p-values, and we're assessing the overall model significance and the contribution of various variables in the model. All right, that's not something that data science focuses on. Data science almost exclusively focuses on prediction, and prediction is exactly what you think it is. It is how well does this model predict on unseen data. It doesn't have to be like in the future or whatever that is. It just has to be on unseen data. How well does it predict various classes or point estimates, whatever that might be? That's mostly the focus, almost all the focus of machine learning as compared to inferential. The thing about this is that it changes the types of questions that you can ask. All right. So typically we're not asking causal questions of machine learning models. There are some methods that do that currently, but they are not used in high volume right now. All right. So most of the goals are centered not necessarily on identifying and understanding which unique features are contributing, all right, to a model. It's more about how well the model is predicting at the aggregate. As an example, if we're, get to the most extreme point, a neural network, we might have millions of weights associated with different classification tasks, right? There's just no way, well, there's maturing ways to unpack that, but typically we wouldn't care that much, like how the model is being learned. We would just care how well it works. All right. So, and we talked about this. It's some of the criteria, like if you have to know, if openness and non-ambiguity is a requirement, then certain machine learning models just aren't going to work. All right. So that's the goal associated with this particular associated with machine learning broadly, all right? Not inference, but prediction. So it's important to understand the differences between those. So typical statistical tests and everything that you've learned kind of your introduction to statistics would fall into kind of that inferential space. All right, a key part of building a solution for machine learning, all right, is to have some type of independent business metric that can be used outside of evaluating the model performance. So there's a whole suite of evaluation metrics to assess how well a model is doing that we will talk about a few weeks from now. That's one criteria. A different criteria is it actually contributing to the problem that we're trying to solve. All right, so there's examples down here. I think the second one is probably the easiest one to talk through, right? We could design a machine learning algorithm, all right, that will identify an email as spam and block it, right? The idea there is that it will, by blocking that particular email, right, they may have viruses, right? And so there should be less viruses in our system, all right? It's not necessarily designed to track the presence of viruses. It's designed to track the presence of spam. But if it does a good job at identifying spam, right, then viruses is a nice correlated effect, right? That's the goal. That we got way too many viruses in our network. We know they're coming from all this spam. Let's get a good spam blocker up there. So by implementing this machine learning algorithm, what we should see is that the number of viruses on the network drops as compared to before it was put into place, right? And that you can test using traditional, means measures, hypothesis testing to say, hey, was there a significant drop, right, in the number of viruses pre and post implementing this machine learning algorithm, which is a great way to think about, deploying machine learning algorithms, all right, to design kind of experimental studies once they're put into place. All right. Some other key terms here, very high level stuff. When we talk about the variable that we're trying to understand, the patterns that we're understanding, it's target. That's our target variable. All right. And features are the things that are going to contribute, all right, to us understanding the patterns of that target variable. In the previous example, the target variable is spam, right? Whether someone is spam or not, right? Features for that particular data set might be when the email was sent, right? The subject of the email, the text of the body, whether it included the word prince, right? So it could be all of these features that you build in order to be able to predict whether that is actually spam or not. Okay, so I think this is analogous to independent dependent variables if people are familiar with that language. So the target would be kind of our dependent variable, and then the independent variables would be the features. Okay, all right. Much of what we think of when we think of classification or machine learning is based off classification. Okay, so classification is the process with which we're basically have a categorical dependent variable, categorical, start using the language, categorical target variable. Our target is a 1 or a 0, or it falls in discrete categories. Maybe that, and might be many categories. It might be an algorithm that's working to define thousands of categories. But typically, a common example is a 1 or a 0, right? So 1 being, that this particular person gets access to a loan, and 0 means that they do not. All right, try to classify that. Or 1 is a spam, and 0 is this email is not spam. Let it go through. All right. Here's some examples here. I'll let you guys read through. Those are pretty obvious. But the important thing here to remember is that the models actually don't predict whether something is a 1 or a 0. They predict the percentage likelihood that that particular row, and you think about it in your data set, it belongs to the positive class. The likelihood that it is a 1. So the output of these classification models are done in percentage distributions. All right, so that distribution, just like any other percentage, is a 1. It's a 0 to 100%, right? Okay. And the threshold, all right, we'll talk about thresholds more and more. The threshold for determining whether someone is or a particular row is a 1 or a 0 is 50%. Okay. So let me show you just a little toy example, right? So say we were trying to decide whether something was spam or not spam, right? And we had 3 emails come in, right? We had 3 emails come in. The data is based off a series of features, right? All right, so these features get passed into our machine learning algorithm. You go in the machine learning algorithm, and out the other side comes percentages, right? So the output of the first one is 51%. The outcome of the next one is 49%. The outcome of the last one is 100%. Okay? So take a second and say to yourselves, now which class are each one of these going to be determined to belong to? Okay? Right? The first one is going to be 1, right? Because it's above 50%. All right? The default threshold for classifying in all machine learning algorithms really is 50%. Any likelihood that one row belongs to a particular class is above 51%, then it gets classified as a 1. All right. The same is true for below 50. If it's 50%, by the way, classified as a 1. All right. So this is 0, and then the model is very certain that this is 1. Okay. So that's how that works. This part of the process is done automatically, but we totally can control where that threshold sits. All right. We'll talk more about that in just a second. The other output, just so we're talking about, is a common approach as well, is just regression. And this is where we're just trying to predict exact numbers, right? So the number of points scored by a player, the amount of rain that will occur, all right? And maybe a person's weight based off various characteristics, all right? So classification, we're thinking about discrete variables, all right? And regression, we're thinking about continuous, all right? Machine learning algorithms can do both. And here we would measure the quality of the model based off how far off those predictions are in a real number sense, all right? All right, so a significant portion of this class, we're going to focus on classification, but I am going to show you regression examples as well, all right? You can think of these 0 to 100 as risk measures, all right? So what's the risk associated with assuming that this model is correct, all right? So if it's 51%, all right, the model's not too sure about that row, right? But if it's 100%, it seems to be pretty confident, right? So the question you have to ask yourself is like, how much risk are you willing to accept, all right? Because you can adjust that threshold up and down. Say, I want my model to be above 75% confident that a particular row belongs to a particular class before I assume that it does, right? And that threshold, right, what level of risk you're willing to accept could totally vary depending on what type of question you're asking, right? If you're asking something medical, right, what is going to be the drug effect, or what's the likelihood that this particular treatment is going to have a positive effect on a patient? Is 75%? Are you comfortable with that? Like maybe that number needs to be closer to 95%, right? But if we're just talking about whether someone's likely to open up an email, maybe it doesn't matter, right? All right. So these are extreme examples, but they are very common, that these types of problems show up, especially when we're thinking about, humans that are involved. We have to be very careful about how we do this. So the percentages that come out of these probability distributions, you can almost think of them as a quantification of certainty or risk associated with each particular item. All right. Well, we're going to dive more into that, but I just want you to understand that in classification, generally the output is not necessarily this belongs to 1 or 0. It's a percentage likelihood, and then it's determined typically at the 50% mark and above. That's when people belong to various classes. All right. Okay. So this is the last slide here for this particular portion of it. All right. So again, we've talked about kind of meta concepts associated with how we're building our approach to constructing a data science problem. One of the two important things to consider in this is data to concept and learning difficulty. Okay. So data concept broadly, is there the data available to be able to support this particular learning goal, right? Does it appear that the data is available? All right. So you just go through these series of questions. Is it large enough? How hard is it to gather? Does the data change rapidly? All right. And do we think this is the right source? So you can go through all these questions. Any one of these is no. You might have to just consider what the realm of possibilities are associated with what you can achieve. Learning difficulty is once you think that you have the data necessary for it, like how complex is the actual task, right? Imbalances in the classes mean, in our spam example, say for instance, we had 98% of the rows in our data set were all not spam, right? And only 2% were spam. That is super unbalanced, right? So it's going to be hard for any algorithm to understand the patterns associated with spam data files if only a very small portion of them are in our data set, right? So we may go back to kind of data to concept goal. We may have enough data, but it may just be highly imbalanced, right? Has this been used in the past, and does it clearly link to the problem? I think these two are highly correlated with each other, right? Do we have examples where this data was used with some success, right? Are there canonical examples that we can point to and say, hey, yes, these features clearly help us understand this particular target var. It's been used in the past with success. We have our own data now, and so we have a certain amount of confidence that it can be done. All right, and is the target variable difficult to measure in terms of it being broken down into smaller pieces? Does it need to be broken down into smaller pieces? Is it just too vague? All right, and then this final question is the one we got to a little bit earlier. What risk are we willing to accept? What are the goals of this particular project, and how can we assess kind of the uncertainty that might be provided through our model, right? Like what is that threshold essentially that we're willing to put into place? All right, so this is phase one. I know that's a lot and it's a real quick. We'll talk more about it on Thursday, but the idea here is to give you some tools to think about when you're developing data related questions, machine learning questions, and give you a foundation and how you would deploy these. All right. So everything from, what is this independent metric? Like what type of question? Is it classification or regression? Do I understand my data enough? And working through all these types of scenarios to be able to measure it. All right. So these are all important questions that you just need to work through in terms of just brainstorming ahead of actually moving into more formal model building processes, which we will talk about next week.